Okay, I'm going to run through a quick summary of some of the key points to come out of paper 1, section A from the mock. Question 1, logs question. The approach, take the 2 over to one side, everything else is already base 4, get it together, collect the terms of the laws of logs, realise that this says 4 to the power of 2 equals this, set that up and you can solve to get 56. Question 2, complex numbers question. The use of the diagrams are crucial here. I can see from the diagram that this argument is going to be negative, this argument is going to be positive. So people who are using the arctan result need to be careful and make sure that their result matches what they know to be true from the diagram. So I want to know the modulus of W. I know that the length of a product comes from the two lengths themselves times together. That comes out. And the argument of a product comes from adding the two arguments together. So obviously you need the correct information here and put it together appropriately there. For part B, the smallest possible integer value such that W to the n is an imaginary number. By imaginary number, it wants a purely imaginary number. So if I know that the argument of W is pi on 12, I've got to work out how this angle becomes up to here. So I need the argument to become pi on 2. I know that when I raise a complex number to a power, I multiply it by the argument. So I've got an argument of pi over 12 multiplied by something becomes an argument of pi on 2. I know that that needs to be then power of 6. So n is 6 for my answer for question 2. On to question 3. Trigonometry one, a number of ways of doing this. One method is here to recognise that 1 minus 2 cos squared theta is actually cos 2 theta. Another method will bring you to tan squared theta is equal to 1. Mistakes to be aware of: if you take in the tan root, then you need to make sure you've got plus or minus there, which will lead you to different answers. Within this method up here, you need to be cautious. If you've got 2 theta, then you need to go twice as far in terms of the domain to make sure that you get all the answers. So the key thing there really was making sure that you get all of the answers. You should have had 4 answers in total, and these are the ones that you should be getting. Question 4, probability question. If you approach it this way, become quite formulaic. I've got 5 boys and 3 girls to choose from, and I want the probability of selecting or choosing 2 girls and 1 boy. So I count the number of ways of choosing 2 girls from 3. So 3 choose 2 for the girls, and choosing 1 boy from the 5. So 5 choose 1. So that gives me the number of ways of choosing this combination. I want a probability, so it needs to be out of the total number of ways of choosing the 3 players. So the number of ways of doing that is 8 choose 3. So set it up as the probability like that, and the answer will pop out fairly quickly. So 5 marks there. On to question 5. 2 distinct real roots. I need to recognise from the question that that's going to be a discriminant question. So set the equation up in the general form: x squareds, x's and numbers. 2 distinct roots needs b squared minus greater than 0. It's a strict inequality. Set it up. Solve the inequality. I end up factorising it. For these, I usually want a little sketch. If I know that it needs to be greater than 0, where is this curve greater than 0? I know it needs to be greater than 9. Got it. And it's greater over here as well. So it needs to be less than 1. So 2 regions, 2 intervals give my answer for question number 5. Question number 6 was the absolute value functions. I know that if I sketch the absolute value of x, I get this. So the absolute value of x minus 1 is just that graph translated 1 down parallel to the y-axis. Similarly, for 2x minus 4, I know that the absolute value of 2x is going to have a gradient of 2. If I move that down 4, then I get this sketch here. Marks there given for 1 for the correct shapes, looking for the symmetry, 1 for the intersects with the x-axis at 1 and 2 and minus 1 and minus 2, and, which is going to be useful in a moment or two, is the points of intersection of the two graphs. Part B asks you for the finite area enclosed between the two graphs. The best way to do this is so I'm actually after the shaded area here. I can use the symmetry to say, well, actually, I just need 2 of this triangle. Well, it's a triangle, so I can do half of the base. I can use that as the base. I know then that that is the height. So I need 2 lots of the triangle, half times the base, which is 3, times the height, which is also 3, comes out to be 9 square units. Question 7, the series. Let me set this up. U2 is 2, so I know that U3 is 2 plus 1 step, so 2 plus D. U4 is 2 plus 2 steps, so 2D. And U8 is going to be the second term plus 6 steps. So I've got that information written down. I also know then that if I want to find the geometric sequence, these are in a geometric sequence, I know that the adjacent terms are in the same ratio. So U4 over U3 is equal to the ratio, and so is U8 over U4. So I can put my information from there into that relationship, and I've then got it. I've got the relationship with D. The next steps are just solving that equation to get D is -3. For part B, it then tells me that UN of the arithmetic sequence is -49. So I need to find N. I can do that. I know U2 is 2. I've just worked out that the difference is -3, so I know U1 must be 5. It's going down in 3s. So I can use that information to find that N is 19. Put that information then into the sum formula for an arithmetic and get the answer of -418. So just putting that solution together slowly to work your way through those parts. Question 8 is the proof by induction method here. Of course, I want to show that this is divisible by 7. So first step, look when n is 1, it equals 7, which is clearly then true for n is 1. The inductive step, assume it's true. Let this thing for a value k be divisible by 7, so let it be equal to some multiple of 7. Show it's then true for the next number up. So let's consider this for k plus 1. I can get this into here. We've managed to rearrange so that I can then substitute in for substituting the assumption in here, such that this bit just matches the 7m. Various ways of doing that step there. A number of people use slightly different solutions. Whichever argument you use, getting that down to be equal 7 lots of something, which you know then is divisible by 7, so you can claim the result is true for k plus 1. You then, for the last step, need to summarize your argument. You know it's true for 1, and you know that if it's true for a number, it follows it's true for the next number, therefore it's true for all n as positive integers. Different ways of phrasing that conclusion, but you have to have a sensible conclusion to get that reason mark at the end of the proof. Question number 9, the integration. I've got a tricky integration to finish section A. Things here, I need to recognise that I can't integrate arctan. So what I need to do is set this up by parts and set it up so that I differentiate arctan. I will integrate x. Now this feels a little bit unusual because I'm making this more complicated. X becomes x squared upon 2. But when I put this into the parts formula, you'll find that the arctan then doesn't need anything doing to it. The thing that's left in the integral is this. Now that's not straightforward either. I need to recognise here that this is actually a top-heavy algebraic fraction. This thing can be written as 1 minus 1 upon x squared minus 1. Now you could do the long division if you wanted to, or whichever steps you use to get to this point here. Once I'm there, of course, I can integrate 1 quite happily, and I need to recognize that this part here, this fraction here, that is the arctan result in trigonometry. So that's going to integrate to be arctan. I can follow those steps through, and I get quite a complicated looking answer there. So a tricky integration to finish section